Hello, I'm Larry Ballou. I'm a solutions architect and lead the training and consulting services for automotive cybersecurity at SAC. I hope that you enjoy this presentation I put together on Automotive SPICE for Cybersecurity Engineering. In this 1-hour session, we'll dive into ASPICE version 4.0, which is the revision of the Automotive SPICE Process Assessment Model, or PAM, and Process Reference Model, PRM, version 3.1, developed by the Working Group 13 of the Quality Management Center, or QMC, in the German Association of the Automotive Industry, or VDA. We'll also touch on ASPICE for Cybersecurity 1.0, which is a separate document. It's not integrated into 4.0 and includes additional updates and plugins to the overall reference model. Enjoy. First, note that ASPICE is an acronym for Automotive Software Process Improvement Capability Determination. Well, the devil is always in the details, which I won't get too deep into here. However, I'll cover enough to help you understand and navigate the concepts of ASPICE. But you like details? Well, besides the ASPICE document, VDA reworked the existing Automotive SPICE Guidelines version 1.0, now draft version 2.0, and referred to as the Blue Gold Book, or BGP, based on ASPICE 4.0. Okay, during this session, I'll cover what is ASPICE and how ASPICE requirements can fulfill some of ISO SAE 21434 work products, the overall process assessment model, or PAM, the process reference model, or PRM, which includes the process categories, the measurement framework, which includes the capability levels, process attributes, and ratings, and finally, how to accomplish the outcomes and achievements of each capability level. ASPICE serves as a roadmap guiding engineers and developers through the intricacies of software and systems development. In 2005, Automotive SPICE was published for the first time by the Automotive Special Interest Group. ASPICE is based on ISO IEC 33000, is a family of international standards developed by ISO that revises ISO IEC 15504 series of international standards. It provides a framework for the assessment of process quality characteristics, and process capability, and organizational maturity. The framework for assessment covers processes employed in the development, maintenance, and use of systems across information technology domain and those employed in the design, transition, delivery, and improvement of services. Results of an assessment can be used for improving processes performance, benchmarking, or for identifying risks associated with the application of the processes. Not that I'm going to go through all the details of all the chapters and annex items now, but here they are represented at a high level. The overall process assessment model, or PAM, the process reference model, or PRM, and measurement framework are covered in Chapter 3, followed by how to achieve each capability level, or CL, for processes for Level 1 in Chapter 4, and process attributes for Levels 1 through 5 in Chapter 5. Yes, soon you'll know the difference between process and process attributes. Finally, I'll cover information item characteristics and key concepts and guidance in Annexes B and C, respectively. Process assessment is a disciplined evaluation of an organization's processes against a process assessment model. The Automotive SPICE Process Assessment Model, PAM, is intended for use when performing conformant assessments of the process capabilities on the development of embedded automotive systems. It was developed in accordance with the requirements of ISO IEC 33004. Automotive SPICE has its own process reference model, PRM, which was developed based on the Automotive SPICE Process Reference Model, now 4.0. It was further developed and tailored considering the specific needs of the automotive industry. If processes beyond the scope of Automotive SPICE are needed, appropriate processes from other process reference models, such as ISO IEC 12207 or ISO IEC IEEE 15288, may be added based on the business needs of the organization. PRM is incorporated in this document and is used in conjunction with the Automotive SPICE process assessment model when performing an assessment. The Automotive SPICE PAM contains a set of indicators to be considered when interpreting the intent of the ASPICE processes. These indicators may also be used when implementing a process improvement program. Here are the abbreviations listed in the document, and I have highlighted the new ones relative to ASPICE. Soon you'll be painfully familiar, sorry about that, with those such as base practices or BP, generic practices or GP, process attribute or PA, process assessment and reference model, PAM and PRM respectively. And I've already introduced you to SPICE or even ASPICE. I like SPICEs. How about you? You may wonder about ISO SAE 21434 versus ASPICE for cybersecurity. However, instead of versus, it's ISO SAE 21434 and Automotive SPICE for cybersecurity. With the sudden emergence of cybersecurity as a requirement in the automotive world, the industry is trying to find the most sufficient and efficient way to achieve their goals. Acquiring a Certificate of Compliance, or COC, for a cybersecurity management system, or CSMS, with ISO SAE 21434 is a popular method to conformity. Yet we also see requests for compliance to the new ASPICE for cybersecurity model. Do you think this is redundant? Well, no, it is not. Rather, it is complementary. If an organization has completed an ASPICE assessment, they have gone a long way to meeting ISO SAE 21434 CSMS compliance. While ASPICE does not cover all the ISO SAE 21434 work products, having implemented ASPICE process outcomes and process attributes achievements, especially to level 3, also places an organization in a very positive light as far as the auditor is concerned. Of course, process capability determination is what the document is all about. At least for software engineering processes for sure, but as you will see now, 4.0 also addresses some hardware engineering processes too. Overall, the model has 3 components, as depicted here for PRM, measurements, and PAM. PRM consists of lifecycle process categories for primary, supporting, organizational, and even cybersecurity now using the inherent plug-in concept. The measurement framework defines the process capability levels and process attributes and also includes how these are rated. The process assessment model ties this all together. Now let's see how all this fits together. I recreated this from the document and we'll use it to keep our bearings on what I'll discuss next. In general, the PAM relationship is the intersection of the X PRM and Y measurement framework axis, and one for each process evaluated, although they could be represented in a single graph as depicted here. The concept of process capability determination by using a process assessment model is based on a 2-dimensional framework. The process dimension on the x-axis is provided by processes defined in the process reference model. The capability dimension on the y-axis consists of capability levels, or CL, that are further subdivided in the process attributes, whereas process attributes provide the measurable characteristics of the process capability. Finally, the process assessment model selects processes from a process reference model and supplements with indicators. These indicators support the collection of objective evidence, which enable an assessor to assign ratings for processes according to the capability dimension. As you will see, indicators are base and generic practices, BP and GP respectively, in combination with information item characteristics, or IIC. As highlighted here, next we are going to explore the process reference model, PRM. ASPICE 4.0 was released in November 2023 and includes the ASPICE process reference model, or PRM, depicted here. For the process dimension, the Automotive SPICE PRM provides a set of process groups as shown in Figure 2. Note that it is basically the same as ASPICE 3.1 with the addition to the process groups for hardware engineering, or HWE, machine learning, or MLE, and validation, VAL. It also scaled back some process groups such as the acquisition, ACQ, supply, SPL, and supporting SUP, whereas the management, MAN, process improvement, PIM, and reuse, REU, are essentially the same. You also may have noticed that some process groups, such as the system, or SIS, software, or SWE, and hardware, or HWE, are represented as a familiar V model, which I'll discuss why following. Also notice how SIS group is positioned over SWE and HWE groups, which I'll discuss next, as described in Annex C1. Processes are collected in the process groups according to the domain of the activities they address. The process groups are organized in 3 process categories: the primary life cycle processes, organizational life cycle processes, and supporting life cycle processes. For each process, a purpose statement is formulated that contains the unique functional objectives of the process when performed in a particular environment. Finally, for each purpose statement, a list of specific outcomes is associated as a list of expected positive results of the process performance. ASPICE for Cybersecurity 1.0 was published in July 2021. What other cybersecurity standards and regulations were also published that year? ISO SAE 21434 and UNECE WP29, R155 and R156 comes to mind. Do you suppose it's a coincidence? Note that ASPICE for cybersecurity does not repeat general processes such as SIS.1 from ASPICE 4.0 or 3.1 for that matter. As highlighted here, ASPICE for cybersecurity both introduced a new process group for cybersecurity engineering, or SEC, and emphasized the processes ACQ2 and MAN.7 for the ACQ and MAN process groups. So those are the only processes discussed in that document. But overall, process assessment module and measurement frameworks are the same. You will always have the system level engineering processes for SIS1 through SIS.5 organized in a system V model as mentioned before. Then depending on what you're developing, you can add on the hardware and their software domain level processes, and perhaps others such as the cybersecurity, as well as to support future processes. All other processes, such as management processes and supporting processes, are system and domain independent and are therefore designed in a way that they can be applied to both the system level and domain levels. First, note that Annex C.2 discusses the concepts of element, component, and unit. I suppose an element can be thought of as an item in the context of ISO SAE 21434, but referred to as a system with ASPICE. As such, an element provides the function at the vehicle level. Along those lines, an element consists of components, which can further be broken down into units, where a unit, such as a software library, is a representation of software element at the lowest level in the conceptual model, which is decided not to be further subdivided, and that is part of a software component. Now, you automotive aficionados will recognize the V model depicted here, where on the right side represents the concept and design processes, and the left side represents the integration, verification, and validation processes. Now you can see it's specifically related to the ASPICE processes, at least for SIS and SWE depicted here. Speaking of verification and validation, tests with ASPICE 3.1 was replaced by verification with 4.0, and 4.0 also added validation. And while verification will help determine if the product was built right, validation will help to determine that the right product was built. In other words, it meets its intended use. As discussed previously, the process groups are organized into 3 process categories: the primary lifecycle processes, organizational lifecycle processes, and supporting lifecycle processes. Here I have listed all the primary process groups that are contained within ASPICE 4.0, which includes the two new process groups for machine learning, or MLE, and hardware engineering, or HLE. The primary lifecycle process category consists of processes that may apply for an acquirer of products from a supplier or may apply for product development when responding to stakeholder needs and delivering products, including the engineering processes needed for specification, design, implementation, integration, and verification. Following, I'll cover each of the primary process groups in a little more detail. The primary lifecycle process category consists of the following groups. The acquisition process group, ACQ, consists of processes that are performed by the customer or by a supplier when acting as a customer for its own suppliers in order to acquire a product and or service. The supply process group, or SPL, consists of one process performed by the supplier in order to supply a product and or service. The System Engineering Process Group, or SIS, consists of processes addressing the elicitation and management of customer internal requirements, definition of system architecture, and the integration and verification on the system level. Finally, the Software Engineering Process Group, or SWE, consists of processes addressing the management of software requirements derived from the system requirements, the development of the corresponding software architecture and design, as well as the implementation, integration, and verification of the software. Still discussing the primary lifecycle processes category, these groups are new with ASPICE 4.0. The validation process group, or VAL, consists of one process that is performed to provide evidence that the product to be delivered satisfies the expectations for its intended use. The Machine Learning Engineering Process Group, or MLE, consists of processes addressing the management of machine learning requirements derived from the software requirements, the development of corresponding ML architecture, the training of the ML model, and the testing of the ML model against ML requirements. Finally, the Hardware Engineering Process Group, or HWE, consists of processes addressing the management of hardware requirements derived from the system requirements, the development of the corresponding hardware architecture and design, as well as the verification of the hardware design requirements. The Supporting Process Group is the second of the three process categories. The first being the primary process group, which I just discussed, and the third being the organizational process group, which I'll discuss following. The supporting lifecycle process category, or SUP, is only a single group and consists of processes that may be employed by any of the other processes at various points in the life cycle. I will discuss more about these soon. The organizational process group is the third of the three process categories. Of course, the first being the primary process group, and the second being the supporting process group, which I just discussed. The organizational lifecycle process categories consist of processes that develop process, product, and resource assets, which, when used by products in the organization, may help the organization to achieve its business goals. Organizational lifecycle processes category consists of the following groups. The management process group, or MAN, consists of processes that may be used by anyone who manages any type of project or processes within the lifecycle. The process improvement process group, or PIM, covers one process that contains practices to improve the processes performed in the organizational unit. And finally, the reuse process group, or REU, covers one process to systematically exploit reuse opportunities in the organization's product portfolio. As mentioned before, ASPICE for cybersecurity added a new primary lifecycle process group for cybersecurity engineering, or SEC, and emphasized two existing processes for ACQ2, supplier requests and selection, and MAN.7 for cybersecurity risk management. The Security Engineering Process Group, or SEC, consists of processes performed in order to achieve cybersecurity goals. And previously, I described the associated ISO SEE 21434 requirements. The Security Engineering Process Group, or SEC, consists of processes performed in order to achieve cybersecurity goals. And previously, I described the associated ISO SAE 21434 requirements. The SEC process category consists of the following. The purpose of the Cybersecurity Requirements Elicitation Process, or SEC1, is to derive cybersecurity goals and requirements from the outcomes of risk management and ensure consistency between the risk assessment, cybersecurity goals, and cybersecurity requirements. The purpose of Cybersecurity Implementation Process, or SEC2, is to allocate the cybersecurity requirements to the elements of the system and software and ensure that they are implemented. The purpose of Risk Treatment Verification Process, or SEC3, is to conform the implementation of design and integration of the components comply with cybersecurity requirements, the refined architectural design, and detailed design. Finally, the purpose of Risk Treatment Validation Process, or SEC.4, is to confirm the integrated system achieves the associated cybersecurity goals. Yes, I did present this slide earlier, but now that you understand a little bit more about the context for the processes, I have repeated it here. Feel free to pause the presentation to further internalize these. As highlighted here, next we're going to explore the measurement framework, which introduced the capability levels. Spoiler alert, there are 6 process capabilities levels, process attributes. Another spoiler alert, of which there are none, and the ratings. The measurement framework consists of 6 process capability levels, 9 process attributes, process attribute ratings, rating and aggregation methods, and the process capability level model. The measurement framework provides the necessary requirements and rules for the capability dimension. It defines a scheme which enables the assessor to determine the capability level, or CL, of a given process. To enable the rating, the measurement framework provides process attributes, or PA, defining a measurable property of the process capability. Each PA is assigned a specific CL. The extent of the achievement of a certain PA is represented by means of a rating based on a defined rating scale. The rules from which an assessor can derive a final capability level for a given process are represented by the process capability level model. The process capability levels and associated process attributes are described in detail in chapters 4 and 5 of the ASPICE 4.0 document. Process attributes, discussed next, are features of a process that can be evaluated on a scale of achievement, providing a measurement of the capability of the process. Process attributes are applicable to all processes. As you can see here, there are 6 capability levels and are listed as 0 through 5. 0 being incomplete is the lowest, and basically means the process is not implemented. 1 being performed means that the process has met the minimum requirements to be achieved. 2 being managed means that the process is more mature in that the process is planned, monitored, adjusted, and its work products are appropriately established, controlled, and maintained. 3 being established means that the process is now implemented using a defined process that is capable of achieving its process outcomes. 3 being a desired level, which is all that a normal organization can expect, whereas 4 and 5 means that the organizations have gone beyond the call of duty, so to speak. Additionally, capability level 3 means the managed process is now implemented using a defined process that is capable of achieving its process outcomes. Notably, capability level 2 means that each project may use its own process as long as the requirements of Automotive SPICE are fulfilled. The capability level 3 requires projects to use a standard process. A possibility to cover variations between projects is to describe tailoring guidelines is allowed. This derived process is the so-called defined process. The defined process has to cover all activities and work products of capability level 1 and 2 for the assessed project. Large organizations would have problems with only one standard process. A single side does not fit all. So organizations are allowed to define several different standard processes. For example, one process for each development site or one standard for each business unit. Within the process assessment model, the determination of capability is based on the 9 process attributes, or PAs. Capability level, or CL, is characterized by one or more PAs whose implementation results in a significant improvement in the capability to perform process. Each attribute addresses a specific aspect of the CL where it is defined. The levels constitute a rational way of progressing through the improvement of the capability of any process. Finally, PAs are features of a process that can be evaluated on a scale of achievement, providing a measurement of the capability of the process, and are applicable to all processes. To support the rating of process attributes, the measurement framework provides a defined rating scale with an option for refinement. Different rating methods and different aggregation methods, depending on the class of the assessment. For example, required for organizational maturity assessments. As you can see here, there are 4 items in the scale, N, P, L, and F, and each is determined by the percentage of the achievement. N for not achieved, meaning there is little or no evidence of achievement of the defined process attribute in the assessment process. P is for partially achieved, meaning there is some evidence of an approach to and some achievement of the defined process attribute in the assessed process. However, some aspects of achievement in the process attribute may be unpredictable. L for largely achieved means there is evidence of systematic approach to and significant achievement of the defined process attribute. L is for largely achieved, meaning there is evidence of a systematic approach to and significant achievement of the defined process attribute in the assessed process. However, some weakness related to this process attribute may exist in the assessed process. Finally, F is for fully achieved, meaning there is evidence of a complete and systematic approach to and full achievement of the defined process attribute in the assessed process. As a result, no significant weaknesses related to the process attribute exists in the assessed process. As depicted here, the ordinary scale just discussed may be further refined for the measures of performed and largely achieved. They are referenced as P plus and minus and S plus and minus respectively. Here, the corresponding refined percentages are displayed in green. Note that the percentages for not and fully achieved, as well as all descriptions, remain the same. Rating and aggregation methods are taken from ISO IEC 33020 and are used to determine whether process and process attributes achieve the process purpose and scope, as well as how the results are or are not aggregated for the rating. Rating method 1, or R1, requires full rating and aggregation across both dimensions, horizontal and vertical. Rating method 2, or R2, as well as R3, are only rate the process attribute level, whereas R2 requires aggregation and R3 does not. Now, honestly, this is a bit more complicated than I can summarize here. But now that you have the basic concept, I suggest you refer to the VDA ASPICE Guidelines section 1.4.4. The process capability level achieved by a process shall be derived from the process attribute ratings for that process according to the process capability level model depicted on the left side of the slide here, and covered in more detail next. The process capability level model defines the rules for how the achievement of each level depends on the rating of the process attributes for the assessed and all lower levels. As a general rule, the achievement of a given level requires a largely or fully achievement of the corresponding process attributes and a full achievement of any lower lying process attributes. Notice how each level includes not only its specific process attributes, but also those of the lower levels. Such as level 2 includes both PA 1.1 as fully achieved and PA 2.1 and 2.2 as largely or fully achieved. As highlighted here, next we're going to explore the overall process assessment model. The process assessment model, or PAM, is a combination of the measurement framework and the process reference model. This entails applying the rating schedule to each of the process attributes for all processes. PAM offers assessment indicators in order to identify whether the process outcomes and the process attribute outcomes, actually achievements, are present or absent in the instantiated processes of projects and organizational units. Assessment indicators are a base or generic practices, BP and GP respectively, in combination with information item characteristics, or II, IIC. More on these following. These indicators provide guidance for assessors in accumulating the necessary objective evidence to support judgments of capability. However, they are not intended to be required as a mandatory set of checklists to be followed. As you can see here, I've added the process attributes, or PA, base practices, BP, general practices, GP, and information items, II, and II characteristics, IIC, referred to as assessment indicators. I have also added outcomes of each process. Regarding the latter, you can imagine how each process can be represented in a single XY graph according to how it has achieved a specific capability level. Corresponding to its level 1 base practices and levels 1 through 5 generic practices for specific process attributes. Note that a specific process attribute, 1.1 for level 1, just requires the process achieves its defined outcomes for base practices and a single generic process, basically indicating the same, both with their associated information item characteristics. Therefore, the only process performance attribute for capability level 1 is PA 1.1 and a single generic practice, or GP 1.1.1, pointing as an editorial reference to the respective process performance indicators. As mentioned before, each process can be represented on a single XY graph according to how it's achieved a specific capability level, or CL, according to its level 1 base practices and levels 1 through 5 generic practices for process attributes. Here you can see the process 1 has achieved capability level 3, whereas process 2 has achieved capability level 2, and process 3 has not even achieved capability level 1. According to ISO IEC 33004, a process assessment model needs to define a set of assessment indicators that explicitly addresses the purpose and process outcomes of the processes within the scope of the process assessment model. It demonstrates the achievement of the process attributes with the scope of the process assessment model, and demonstrates the achievement of the process quality levels within the scope of the process assessment model. The assessment indicators generally fall into 3 types of practices that support achievement of either the process purpose or specific process attribute, information items and their characteristics that demonstrate the respective achievements, resources and infrastructure that supports the respective achievements. In the assessment model, only practices and information items are used. Practices representing activity-oriented indicators, where information items representing result-oriented indicators. Both practices and information items are used for judging objective evidence to be collected and accumulated in the performance of an assessment. Practices support achievement of either the process purpose for base practice or the specific process attribute for generic practice. Base practices, or BP, apply to capability level 1 and provide an indication of the extent of the achievement of process outcomes. Base practices relate to one or more process outcomes, thus being always process-specific and not generic. Generic practices, or GP, apply to the capabilities level 1 to 5 and provide an indication of the extent of process attribute achievements. Generic practices relate to one or more process attribute achievements, thus applying to any process. Hence, they're generic. A second type of assessment indicator, information items, II, and their associated characteristics, IIC, are all listed in Annex B. These are meant to offer a good practice and state-of-the-art knowledge guide for the assessor. Therefore, information items, including their characteristics, are supposed to be a quickly accessible information source during an assessment. Work products are produced by the organization assessed when performing, managing, establishing, analyzing, and innovating processes. Information item characteristics shall not be interpreted as required structure of the corresponding work products, which is defined by the project and organization respectively. Finally, it's kind of confusing that ASPICE for cybersecurity engineering has no mention of information items and just refers to them as work products. Sorry about that. Capturing experience acquired during product development, i.e. at the doing level, in order to share this experience with others means creating a how level. However, a how is always specific to the particular context in which a company, an organizational unit, or a product line. For example, the how of a project, organizational unit, or company A is potentially not applicable to, say, a company B. However, both might be expected to adhere to the principles represented by PAM indicators for process outcomes and process attribute achievements. These indicators are at the what level? While deciding on solutions for concrete templates, proceedings, and tooling, etc., is left to the how level. Now that you understand a little bit more about the process reference model, PRM, and the measurement framework, and the process assessment model, PAM, let's discuss how to achieve capability level 1 using process performance indicators at the process level. On the left side here, and capabilities level greater than 1 using process capability indicators for process attributes on the right side here. First, for capability level 1. I introduced you to these when we discussed the process reference model. Now let's look at how a process within a group is addressed to conform with level 1 outcomes. I'm only going to cover one process for ACQ4, supplier monitoring, so you understand the general structure that ASPICE uses for each and every process. Otherwise, this presentation would be 4 hours instead of 1. It's interesting to note that the capability of a process on level 1 is only characterized by the measurement of the extent to which the process outcomes are achieved. However, according to ISO 33003, a measurement framework requires each level to reveal a process attribute. Therefore, the only process performance attribute for capability level 1 is PA 1.1, which only has a single generic practice, a GP 1.1.1, pointing as an editorial reference to the respective process performance indicators. The process reference model and performance indicators for level 1 are discussed in ASPICE 4.0 Chapter 4 and ASPICE for Cybersecurity Engineering Chapter 2. Here I'm only going to cover one process for ACQ.4, supplier monitoring, so you understand a general structure that ASPICE uses for each of the processes. Note that base practices, or BPs, as mentioned previously, are only relative to level 1, indicating there is at least a performed process in place. You can say that it's a minimum requirement for complying with ASPICE, whereas achieving higher capability levels require additional process attributes to be achieved. I'll discuss more on that in a subsequent section. Each process consists of a defined ID, name, purpose, outcomes, various BPs, and output information items, i.e. work products. BPs are indicators for the achievement of the process outcomes and may be regarded as requirements. I will cover each of these on the following slides. The process for supplier monitoring is assigned process ID ACQ.4. It has a simple process purpose to track and assess the performance of an external contract-based supplier company against agreed commitments. As such, it can be mapped to ISO SAE 21434 work product WP0701 for establishing a cybersecurity interface agreement, or CIA, related to base practice 1 covered next. ACQ4 process outcomes consist of the following. Number 1, joint activities as agreed between the customer and supplier are performed. 2, all information agreed upon for exchange is communicated regularly between the customer and the supplier. 3, performance of the supplier is monitored against the agreements. And 4, changes to the agreement, if needed, are negotiated between the customer and the supplier and documented in the agreement. As mentioned previously, base practices, or BP, apply at capability level 1 and provide an indication of the extent of achievements of the process outcomes. ACQ4 consists of 5 base practices, BP1 through BP5. Of course, other processes have their own and obviously different base practices. Most have more, but some have less. For instance, SYS1 has 4, while SPL.2 has 8. I'm not going to repeat all those here, but next you'll see how the BPs and the information items are mapped to each of the outcomes, 1 through 4 for ACQ4. Base practices and output information items are mapped to their desired outcome to achieve. All must achieve the desired outcome to be considered as complying with capability level 1. The document lists a spreadsheet-like table that shows which IIs and which BPs must meet the required outcomes. Speaking of information items, or IIs, more on that next. An information item, or II, is a separately identified body of information that is produced, stored, and delivered for human use. Human use includes the information stored, managed, and processed by a tool. Characteristics of IIs are defined using the scheme in Table B1 and Annex B, but I have only represented 02-01 and 03-05 here. Each entry consists of an information item identifier, IID, information item name, and information item characteristics, or IIC. Now that you understand how to achieve capability level 1 using process performance indicators, let's discuss how to achieve capability levels greater than 1 using process capability indicators for process attributes. I will now cover the process capability levels and process attributes for levels 1 through 5. Process attributes, or PAs, defines the generic practices, or GPs, and information items and their mapping to the process attributes for each capability level defined in the measurement framework. Similar to covering only the ACQ4 process previously, I'm only going to cover one process attribute for PA 2.1, Process Performance Management process attribute, so that you understand the general structure that ASPICE uses for each and every process attribute. Each process attribute consists of a defined ID, name, scope, achievement, various GPs and output information items, i.e. work products. GPs are indicators for the attainment of the process outcomes and may be regarded as requirements. I will cover each of these on following slides. But first, it is interesting to note that some of the differences between the performance indicators for level 1, as previously discussed, and the process attributes for levels 1 through 5. Whereas the former provided a purpose, the latter provides a scope. Also, the former provided an outcome, and the latter provides an achievement. A minor detail, I suppose, but it is what it is. First, note that there is no PA0 process attribute for process of capability level 0. That's because the process is not implemented and or it fails to achieve its process purpose. Meaning at this level, there is little or no evidence of any systematic achievement of the process purpose. Finally, due to lack of a defined process attribute for process capability level 0, no generic practices and information items are defined. I presented this graphic before, just as a reminder about it. Except for level 0, just discussed, each level 1 through 5 has one or more process attributes, or PAs. Notice how each level includes not only its specific PAs, but also those of the lower levels, such as level 2 includes both PA 1.1 as fully achieved, and PA 2.1 and 2.2 as largely or fully achieved. And notably, the lower level PAs are required to be fully achieved, as opposed to largely or fully achieved for the current process attributes. The process performance management process attribute is assigned process attribute ID PA 2.1. It has a simple process attribute scope, such as the performance management process attribute is a measure of the extent to which the performance of the process is managed. PA 2.1 process attribute achievements consists of the following. 1, strategy for the performance of a process is defined based on identified objectives. 2, performance of the process is planned. 3, performance of the process is monitored and adjusted to meet the planning. 4, for human resources, including responsibilities and authorities for performing the process are determined. 5, physical and material resources are determined. 6, persons performing the process are prepared for executing their responsibilities. 7, physical and material resources for performing the process are identified, made available, and allocated and used. And 8, interfaces between the involved parties are managed to ensure both effective communication and the assignment of responsibilities. As mentioned previously, generic practices apply to capabilities levels 1 through 5 and provide an indication of the extent of process attribute achievements. PA 2.1 consists of 6 generic practices, GP 2.1.1 through GP 2.1.6. Of course, other process attributes have their own and obviously different generic practices. And it's notable that generic practices are not specific to a process. That's why they're considered generic. Rather, they're specific to a level for all processes. I'm not going to repeat all here, but next you will see how the GPs and IIs are mapped to each of the achievements, 1 through 8 for PA 2.1. First, here are the remaining GPs 2.1.3 through 2.1.6 for PA 2.1. I'll list them here just for completeness, and I'm not going to repeat them all here. Generic practices and output information items are mapped to their desired achievement. All must support the desired achievement to be considered as complying with its associated capability level 1 through 5. In the example CL2, which also includes PA 1.1 and PA 2.2, as mentioned with base practices, the document lists a spreadsheet like a table that shows which IIs and which GPs must meet the required achievements. Note that BP outcomes versus GP achievements, they're like potatoes versus potatoes, so to speak. The last topic I'll cover is traceability and consistency as represented in ASPICE 4.0, Annex C5. I say represented since the document does not do too much to describe it. However, the VDA Automotive SPICE guidelines I mentioned previously does in section 2.1.6 base practices on consistency and traceability. So why should you put effort into traceability and consistency? Well, ASPICE also requires that you ensure traceability and consistency between your system requirements and stakeholder requirements. Traceability can be established through hyperlinks such as doors, through specific traceability tools such as Rectify, through traceability matrices, or through other manageable means which are supported by your company's tool landscape. The purpose of traceability is to, one, support consistency checks, like for instance, to verify the completeness and accuracy of system requirements. Two, to support the impact assessment in case of change requests or deficiencies. And three, to support the reporting of stakeholder expectations. The second part of this aspect is of consistency. Consistency means you have to ensure completeness and correctness of your system requirements against the stakeholder requirements. As this process is your entry into your development, you want to ensure that your system requirements are covered in stakeholder requirements correctly. Finally, in Automotive SPICE, consistency must be fulfilled as required by the traceability consistency base practices in MAN 3 or the CIS, SWE, or HWE processes. So there you have it. I hope that you enjoyed this presentation I put together on Automotive SPICE for Cybersecurity Engineering. Please reach out to me at SAC to discuss how we can help your organization to ensure that your products are secure by design. Thank you for your time.